Okay, so we're looking at this point right here. Now, the first thing that we can consider um, is this, does this have high leverage? So if I'm looking at this, high leverage would mean it's outside of this range of x's. It falls right within it. So I would say it's not high leverage. So anything that says that, I'm going to rule out. So these two are no good. Oh, you know what? That one thing alone kind of gives me my answer. But, we can make sure the rest of it's correct. Is it an outlier? Well, it's definitely far removed from what we'd expect from the trend line. So that works. Is it influential? Well, there's no doubt that without that point, our regression line would be right there. Now it's probably going to be more like that. I don't know exactly what. So I would say all those apply, and C is the correct answer here. Okay. So if you were looking at one of B or D, which was the other popular one, especially D, that's mostly right, except it doesn't have high leverage. Leverage specifically means if here's where the main clustering of data is in the X direction, it would have to be over here or over here, somewhere away from it, left or right. Okay. Okay, so here's what we're doing today. You can see it's a bunch of notes about stuff we've covered. And a lot of this, are specifically things that you could use as reference for, they're almost like reference sheets you could use for the test, just to go over as you're looking at your homework, even while you're going through the test. So anyways, hopefully it's helpful. A few new things that maybe I failed to cover before. So let's just jump right into it. So the first thing, just in general, is that the AP formula sheet that I hadn't really gone back and checked over, but I did last night, and I saw, luckily, it has your regression equation given. It has this equation, which is when you plug in your y bar and x bar when you're trying to solve for. You would use this when you're solving for the unknown y-intercept. And then it has your slope formula. So you don't have to have those memorized even when you take the AP test. And again, I encourage as many of you as possible to take that AP test, but we'll talk about that more another time. Here's your sample standard deviation formula, which this one and your correlation would really only be needed for interpretation problems, not to plug numbers in and solve anything. And this right here is, again, maybe just an interpretation problem. This is for your X bar, it's the average. Okay, so AP Classroom, and everyone needs to sign up for that. I might need to take some time in class to actually force everyone to go in and do that. They've already started introducing some video overviews of all the topics that we cover in AP Statistics. Right now they only have Unit 1, so it is not going to cover the stuff that we're doing right now. So it's not good for this test, to go back and watch those. But when we get to the point, especially next semester, those of you doing the AP test, if you need to go over, they're like quick videos that you can kind of review some of the concepts. Okay, just want you to be aware of it. I'll try and make those better known as we move forward. Okay, so notes about scatter plots. This is kind of a recap of things, but some of the stuff maybe I just want to make explicit. You need to carefully identify your explanatory and response variables. Explanatory will go on your x-axis, response will be your y. So which one makes the most sense to use as a predictor of the other? And that's going to be your explanatory. So the clues that you can look for, if in the problem it says something about what percent of the variation is explained, then you can use that. So it might say 23% of the variation of housing price is explained by the model. Well, if it tells you that, then you automatically know in that particular problem, housing price is your y value. It's the response variable, because R squared always explains the variation of your y values. Okay. And even if the problem doesn't require it, draw a sketch of the scatter plot. So, you might tell yourself, okay, so that's the explanatory, this is the response, but go ahead, take it, it takes like 10 seconds. So I would put, okay, so income is my explanatory, and whatever, size of house is my response. So, just draw something like that, and then that'll just help you kind of think through how the X and the Y work. Okay, so hopefully that's clear. Duffs, don't forget that. You need to make sure you're explaining direction, unusual features, form, and strength. The one thing to add here is that AP really only uses these 3 adjectives when they're describing a strength. So in general, you can just think about it. A strong correlation is going to have small residuals. A weak one will have large residuals. Again, if I kind of make up a scatter plot right here, this we can see we're going to have big residuals. But if I had another one right here, these are all small residuals. So this is a strong correlation on the left and a weak correlation on the right. But just to make that visible, what we're referring to. Okay. This is a random thing. I don't think this would ever come up on the AP test, but it's worth mentioning just for you to know. So if every point on a scatter plot fell in perfect line with the other, then we have a perfect correlation. All right, so it doesn't matter how steep that is. If I had, try and draw these dots pretty big, this barely steep line right here, but they all happen to fall exactly in line, that is a perfect 1 correlation. It could be a negative direction, so it'd be a perfect -1. There is an exception, and that is if all the points in the scatter plot fall perfectly in a horizontal line, there is a correlation of 0. So this, correlation of 1. This, correlation of 0. And the reason for that, there's 2 ways of thinking about it. A correlation shows the strength of the association between a change in X and a change in Y. There's no change in Y. So therefore, it doesn't matter how X changes. It has no impact on the value of Y. So there's 0 correlation. The other thing, just consider the actual formula that we use. So right here, if every value of Y is the same, well, then this value and this value will be equal. So it cancels out to 0, and that means the entire correlation is simplified down to 0. So there you go. Anyways, like I said, probably would not appear on the AP test, but it's worth knowing. All right. Get out of there. Okay. So this is another random thing. Why is this called regression? It's basically the idea that if you, especially like things genetics or anything that generates a future offspring of some kind, plants, humans, that if you have an extreme outlier value, the offspring is going to tend to fall back toward the mean. If it's an extreme low outlier, it's going to fall back toward the mean by being higher. If it's an extreme high upper outlier, it's going to tend to fall back to the mean, being lower in the next generation. So they regress, and the idea is more or less true as far as how it plays out in real life, but that's just the idea of where regression comes from. And now we're stuck with the term. Okay, the least squares regression line. This is all review stuff right here. This is a line that minimizes the sum of the squares of the residuals. It's important you understand that that's what that means. Correlation coefficient. Now we had the entire list of correlation properties. It's page 156 in your book. Here's just a couple of them. The sign of the correlation is the direction of the scatter plot. If you see any value for correlation beyond those bounds, then it's incorrect, and you can kind of comment to that now. What happened? That's not what I wanted. Okay, sorry about that. Anyways, the coefficient of determination, that's R squared, is a percent explaining the amount of variation of the response variable. So I have a few of these interpretation templates. So you could say this a couple different ways. So blank percent of the variation in the response variable is explained by the model. You could also say, we haven't really done it this way, but blank percent of the variation in the response variable is explained by the variation in the explanatory variable. So I don't have an actual example where I plug in some context, but I do for some other templates, so we'll see that. The regression equation given right here. And one thing, this has come up, and so it's caused a little bit of confusion. Remember, in the textbook is b sub naught and b sub 1 times x. We could call these whatever we wanted, as long as it's not like a reserved term like y or x or r. But if we wanted to call it c and d, there's nothing really wrong with that. We could do it. But this is how AP presents the equation, and so that's how we're going to kind of approach it. The other thing that can cause some confusion if you're looking at other places on the internet, sometimes people write it as ax plus b, in which case slope and y-intercept flip. Whichever letter is in front of x is your slope. Okay, hopefully that's good. Talking about the y-intercept, which for us is a, it's the constant right here. Sometimes you're asked to interpret the y-intercept, and sometimes that interpretation makes no sense. So if we were going to have a regression comparing shoe size to IQ, well, you know, you could wear a size 9 shoe, you might wear a size 12 shoe, but no one wears a size 0 shoe. So a 0 y-intercept doesn't make any sense in this context. So you could say something to that effect. Like if it says, or write an interpretation of the y-intercept for this problem. Say, well, according to the model, 0 would result in this IQ, but it doesn't make any sense because there's no size 0 shoe, at least so far as I'm aware. I've never seen anything like that. But, you know, then sure enough, someone will come out and say, oh, there's a size 0. So anyways, in this context, at least according to everything I know, 0 doesn't make any sense. So if we do want to write an interpretation, we can use this. I'm only going to talk about the one where I filled it in. According to the model, we would expect a value of blank for salary when level of experience is 0 years. And yeah, just to reiterate, if it doesn't make sense, say that it doesn't make sense. But here, this is totally fine to have a y-intercept for that context. Okay, now we've got the slope. And again, we can interpret the slope. According to the model, a test grade goes up 0.64 points for every 1 point increase in homework grade. So the template that you used right here, you know, it could go up or down based on the sign of the slope. If it's a negative, then it will go down for every increase in x. All right, so keep that in mind. The other thing that was kind of causing some confusion, remember with your units for slope, it's going to be units of y over 1 unit of whatever your x is. So that's going to be your slope unit. Okay. Any questions so far? Okay.
So if the y-intercept doesn't make any sense, should we just like say like the y-intercept doesn't make sense in this context?
Yeah, and explain why it doesn't, like in that thing I gave, because there's no size 0 shoe. Sometimes if you're talking about, if we were talking about high school exam scores, like how people did as freshmen, sophomores, juniors, seniors, we have 9th, 10th, 11th, 12th, or, you know, whatever your age, maybe we go down and we include 8th, 7th, and 6th grade. Well, if we extended this down to 0, there's no 0 grade. And so that also wouldn't make sense as a y-intercept, though we do have it just to make the rest of the regression model work.
Yeah.
Okay.
Perfect, thanks.
Yeah. Okay. So as far as this goes, for the slope, you do have this formula. I'm trying to think if there's anything important here. We talked about this and we had some examples of it. If you were only given r squared and you have to figure out r, and hopefully you guys learned some lessons about this from the other day, make sure you decide whether it's going to be a positive or negative correlation. It's going to be positive right out of the calculator, but you need to decide, should it actually be negative? And you have to think through that, so take the time to kind of think about it. Okay, and here's a couple of examples, things that might be positive or negative correlations. But the bottom, another way to think about correlations is a positive one would be as the explanatory variable goes up, the response variable also goes up. A negative would be as the explanatory goes up, the response variable goes down. So just kind of keep that concept in mind. All right, questions on this? Okay. So the other thing we talked about is here's your generic regression equation, but a lot of times for FRQs, that's not going to be good enough. You might get a lot of the points for the FRQ, but to get full points, they're going to want you to put this into context. So now we could maybe switch it out with this. So the predicted weight equals, these coefficients that we come up with, but we also include some units and we talk about whatever the explanatory input would be, the height of someone. Okay, so keep in mind, and we already did kind of a few examples like that. So yeah, don't know what else to say about it, but there you go. Okay, really not going to talk about this, except this is, like I said, kind of some reference pages almost for you to kind of think through all the stuff from this unit. So here are your regression assumptions. So if you have a question about it, does it make sense to use a linear regression for this data set? You can kind of go through this. Is it quantitative? Is it linear? Do I have outliers? Is there equal variance in my residual plot? And the one thing I'll add to this is make sure you check your scatter plot to check for linear form. And in a problem like this where they ask if it's appropriate, they'll probably give you most of the information to work with. So you can kind of check all your sources. Extrapolation. This was just yesterday. So basically extrapolation is not preferred because you have a lot of uncertainty as you stretch your model beyond your data. But if you're just barely extending it, it's potentially useful. Okay, so this is and we've looked at this a few times, but if you have a printout, and like we talked about, there are different programs where you need to get used to reading stuff like this, because this probably won't be the last time you ever see anything like it in your educational career. So you need to, what I think is easiest is identifying the y-intercept first, which will either be labeled as constant or intercept. And that means that the other coefficient given right here is your slope. And I don't know what the context of this problem is, but it's going to be related to caffeine. As your caffeine changes, something else is going to change as a result. Okay, now the other stuff in these printouts that can be useful, you might see R, though a lot of times they don't show that. They are showing R squared. And you can see there's two R squareds here. R squared is the one we want to use. R squared adjusted, you want to avoid. That's only if you're doing multiple regression. And that is not part of our course at all. So R squared is what you're always going to be looking at. The standard deviation of the residuals is just going to be labeled as S. And remember, that can be useful for certain analyses. Okay. So right here, this type of problem, we went over one of them in class, but I just wanted to go through another example real quick. For every one standard deviation, and x value is away from the x bar, the predicted value, y value that is, will move r times its standard deviation up or down, depending on the sign of the correlation. So just to talk about this, there is a correlation this girl found between the attendance at a World Cup soccer match and the number of goals scored. It's not much of a slope, and it doesn't tell us the R squared, so we don't know how good the model is. But let's say it's a good predictive model. So let's say, given this regression model above, what could you say about the number of goals scored in a match that's 3 standard deviations above the mean for attendance? So again, like I said at the beginning, drawing a diagram, drawing a quick scatter plot might help. So I know that attendance is predicting the goals scored. So as the attendance, because it's negative, as the attendance goes up, goals scored go down. I know it's very slight, but we'll just draw it exaggerated. So as attendance, let's say the mean is right here. As this goes up 3 standard deviations, so 3 times the standard deviation of x, it looks like it's going to go down, not 3 standard deviations of y, but 3 times r times the standard deviation of y. So we could just say something to that effect. So how would we want to phrase it? What could you say about the number of goals scored? The predicted number of goals scored in this match would be 3 times r times the standard deviation of y, lower than y bar. Okay, so questions on that? Okay.
I'm sorry, what is it says SE coefficient?
Oh, yeah. That is not for us. This is the standard deviation of the errors in the one variable. And so we wouldn't actually use this. There would maybe be more of the printout below that just says S, and that would be the standard deviation of the residuals that we would use. That's a good question.
Got it, thank you.
Okay, so residuals. This is something that I kind of skimmed over, and I realized maybe I needed to spend a little bit more time talking about it. So we do have an actual residual formula, which is not on the formula sheet, but it is one that you need to understand. It's always the actual value minus the predicted gives you the residual. It's one of these topics that, when it's explained, it's so simple seeming that it also can be like we don't give it enough time and emphasis, and it can sneak up on us and be like, oh, this is actually kind of a challenging problem. Okay, so when your residual is positive, the model underestimated. So in context, it makes a little more sense. If you had a residual of +7, that means the actual value is 7 above what the model predicted, and therefore the model itself underestimated what the actual value, compared to the actual value. Now, the opposite is also true. Negative means it overestimated. So a residual of -7 means the actual value is 7 below what the model predicted, and therefore the model overestimated. So it might be one you need to pause for a second and kind of think through, even draw a diagram. Be like, okay, so if this is where the point was, so I have a negative residual. Okay, that looks like that's an overestimate at that point. So it might be worth it just to sketch something down on some scratch paper and kind of think through it. Okay, so these are a couple of problems that we haven't as a class really gone through, at least not in, I think we did one similar to it. But if you know a regression equation and you know a residual, you can work backwards to find an actual y value. Okay, so to do this, and I didn't put context in this problem, but they might have given us some specific context. So we need to first of all remember these two formulas, which again, the regression equation is given to us. And we need to remember that the residual is the actual minus the predicted. So we'll need both of those formulas to help us get through this. So the first one, okay, it tells us we have a residual. We'll worry about that later. but the X value is 28. So what we always need to start off with questions like this is figure out what is the predicted value for that input. So I can just plug that right into my regression equation right there. So y hat will equal 42.34 minus 0.537 times 28. All right, you guys can do that calculation. All right. And someone else can go ahead and plug the number in on the screen. Perfect. 27.304. So now if we have a 4.21 negative residual, what is the actual y value? Here's the predicted y value, y hat. So we need to understand that notation. So now let me plug this into this equation, the residual one. So I know the residual is negative 4.21. I know the predicted value is 27.304. So now I just want to figure out what is the actual y value. Well, you guys can do that. So as soon as you guys have worked through that algebra, someone can plug in the number. All right. Getting a few answers, but they're all coming out the same and I can read them all. So that's good. Very good work. So that is what we would do. Of course, if there was context, we would then use the units for whatever y was. So there it is. 23.094 is the actual value that would give us a residual of negative 4.21 if its associated x value was 28. Now we can do the same thing. I'm not going to actually do the calculations on this one, but I'll just set up the problems. Using the same regression equation as above, you have an x value of 16 and a y value of 36.44. What is the residual? So the important thing to point out is that this is an actual point. That's an actual dot on your graph. And so if you're trying to figure out the residual of it, you need to figure out the predicted value that would happen at the x value first. So even though 1636.44 is your actual point, we're only worried about the 16 to start off with. Because our y hat equals 42.34 minus 0.537 times 16. I'm not going to worry about that. Once we get this number, then I can go, and what I don't know for this problem is the residual. But for this, I do know the actual right here. So now I can plug that in, 36.44 minus whatever the result of that calculation above is. So I'll just put y hat. So as soon as I know what y hat is, I'll plug that in and that'll tell me the residual. So there are questions on these types of problems. Okay. So there is a lot going on with this template. So it's maybe easier just to look at this and then you can kind of do some reverse engineering and figure out how I came up with this. So the actual weight of, and I didn't provide the whole problem, but let's say I need to interpret the residual. I could say something like this. The actual weight of this elephant at 10 years old was 12,458 pounds. This was 643 pounds under the predicted value of 13,101 pounds, which means that the model overestimated. All right, you can kind of see how this template is being used to generate this result, response. So again, use this just to help you and guide you along the way. So I don't know if there's more to say about that. Okay, the unusual features. We're gonna have a little bit more fun here. So we talked about these yesterday. This is almost, I just copied a slide, but I changed it a little bit. So influential point is basically one that changes the regression model greatly if it's removed. This is a key thing, and we did talk about this yesterday, but high leverage points and outliers can be influential or not depending on a number of factors. And high leverage outliers are always influential. So be on the lookout for those. So this is where it's going to be a little bit interesting. And you don't need to like say anything right now, but I'm about to show you 4 data sets that have the same summary statistics. There's going to be a mean X of 9, a mean Y of 7.5. There's going to be a correlation of 0.816, the exact same regression line. And of course, the coefficient of determination would have to be the same if the correlation is the same. So I want you to imagine for about 15, 30 seconds what these 4 data sets are going to look like. And hopefully your brain is still functioning well enough at this time of the week, because mine's pretty much shut down. All right, hopefully you have some kind of a mental picture of 4 different data sets with the same summary statistics, and here's the actual result. And this is not a hypothetical, this is real, these are real data sets that do have the exact same summary statistics. And you know, we can comment on these if you want to like put something in the chat, or if you want to say something about any one of these graphs, something that stands out to you in any one of these 4 graphs. Scatter plots, I should say.
It's just crazy. Like the 4th one is literally a vertical line, yet it has the same summary statistics as like number 1, which is like kind of regular, like scatter plot. It's crazy.
Yeah. And yeah, absolutely. So this one, you got this weird point right here, but this kind of, and the reason I kind of threw this in right here, first of all, this is called Anscombe's quartet. And so a guy named Anscombe kind of came up with this idea. But this also is good to throw in here because it's showing just what 1 point can do. So without that point, it's a vertical line, and that's not, I don't even know how to interpret a vertical line on a scatter plot. But yeah, we can see the power that is definitely an influential point. You can describe it more. Any other oddball points or other observations here? So if we talk about this one, what do we notice about up here?
It shouldn't be represented by a linear line.
Exactly. So it's non-linear, so this linear regression isn't appropriate. I would be willing to bet that whenever I asked you guys to envision 4 data points with the same summary statistics, you imagined 4 different data sets that looked something like this, just with the points moved a little bit. And so this kind of just speaks to the point that we cannot make assumptions about the data set without having seen it, without having seen the scatter plot. All right, and so just to finish this up, what would you say about this right here?
It has an influential point.
As an influential point, definitely. What else? How else would you describe? I'll go ahead. We know which one we're talking about here. So how else would you describe that using other terms?
It's an outlier.
Okay. Does it have leverage?
No leverage.
No leverage. There we go. All right. So just a couple of concepts embedded in this. So I thought it was worth diving into a little bit. Okay, let me see. Yeah, and there's kind of the takeaway, one of them. All right, so there's going to be about 8 multiple choice problems here. Luckily, and you'll need to plug this into your calculator. And I want you to, we're going to use the same data set over and over again, so you're not going to have to re-plug stuff in, but plug this in the first time and look at the question and answer it. I'll bring the poll up in just a second. So the most common answer was, let me close this down, this one right here. And so just plugging this data in, once you got your 2 lists, you just need to make sure you're running that linear regression stat calc number 8 and pick the correct list. You should see your R value right here, and that is the correlation we're looking for. So there are some other values there. If you pick the wrong one, then of course that might be why you got the answer you did. All right. Yeah, and if at any point you need to fix something with your calculator, you know, go right for it, because yeah, these batteries can run out of, or these calculators can run out of batteries. Okay, let's jump ahead. I'm about to change the question, and the question just changed. Make sure you see that. All right, so not much difference in this problem right here between the last one, except now it's asking for the slope. So when you look at your regression output, and it has your A, B, R squared, and R, we're looking at B, which is our slope. And so whatever this number is your answer, which should have been D, negative 1.529. Okay, and last, well, not last question, there's quite a few more questions, but next question, I should say. The thing you have to interpret here is that it's saying what % of the variation of y is explained by the variation in x. This is another way of saying what's your r squared. And again, you got a, b, r squared as the third one, r down here. So whatever that says is going to be presented as a %, which should have been b, 88.9%. Okay, so not much to it. We will use this data set again. I think we're done with the questions on it for now, but it'll come back later. So anyways, now we've got more conceptual questions to think through. Okay, so this is really just kind of getting us to think about what correlation means. And the basic idea, a positive correlation means we have, as your explanatory variable goes up, so does your response variable. So if height, if we're using that as the explanatory variable and time on court is your response, we're going to have a trend line like this. And that means we can kind of go through. There is no relationship between height and time on court. Well, I think we proved that there is one. All right, so that doesn't make sense. Taller players tend to spend less time on the court. So the taller you are, well, it looks like the more time you spend. So that's not right. Because the correlation is positive, the association is nonlinear. Well, that's not true. I will say only knowing the correlation means you still need to see the scatter plot, but for this problem, that's not an issue. Shorter players tend to spend less time on the court. Well, yeah, that seems to be true. So there's your answer. Okay. So this one, the context might make it a little bit challenging, but see if you can work through and figure this one out. And like I suspected, this one caused a little more confusion maybe than some of the other problems have. Part of it is the context, and like literally what happens if a stock is split, they actually take whatever the stock share value is and they just frequently they'll split it in half. So they'll just cut that value in half. So let's kind of create a scatter plot. So here's pre-split, here's post-split, and we're going to use simple numbers here. Let's say we got a $1, $2, I'll put the units, $3, and $4. Now we've got, after the split, we've got our $1 and $2. So after your $1 stock is split, it goes to 50 cents. After your $2 stock is split, it goes to $1. 3 goes to 150, 4 goes to 2. And you can see, if we're looking just at the scatter plot, there appears to be a perfect correlation between those. And that would be true because we actually have a function that defines how this value is derived from the input. So it is strictly an algebraic function going on here, so it would be a perfect correlation. So it's tricky because the most common wrong answer is B. Now I should say that's wrong. It is actually, statistically, it is a perfect correlation. So the correct answer is D. And you guys did really well. That was the majority answer. Sorry, not the majority. It was the plurality answer. It was the most commonly picked one. So hopefully, are there questions on this? Because this concept's a little bit confusing maybe at first. Okay. I'm not hearing anything yet, but if questions come up or if you want to come back to it later, we can do that. Okay, next question right here. Take a little bit of time, think on it. So I will say, kind of in looking at this question, I wrote this one last night, and in looking at it a few times, there's almost 2 correct answers here. So we'll just kind of talk about what the answer should be and why another one is kind of acceptable. So a book publisher thinks there's a linear relationship between number of pages in a book and book sales. If this is correct, what should the residual plot look like? Now, the assumption here is that we're talking about a scatter plot. So you might decide that for yourself that longer books sell more, or you might decide it's a negative correlation and that longer books scare people and they look for those short books. So maybe it would be a negative thing. But anyways, if there is a linear relationship, whether it's positive or negative, the residual plot should, sorry, just a second, should show something like this. So the best answer, the one that I intended to be the answer here, was A. There should be even scattering throughout, above and below 0 for the entire length. Okay, now we don't want to see a straight line with a positive slope for the residual plot, and that's the key to this. The scatter plot, that would be fine. The point starting close to 0 and getting progressively further away, well, if that happened, we have this sort of thing like that, and we never want to see that in a scatter plot or in a residual plot. So the one that is kind of acceptable as correct, and I think AP maybe does a better job than I do of phrasing it so that's not ambiguous like this, where it says every point should be exactly 0. If you were thinking of linear relationship as though it's algebraically defined and there's a definite amount of books sold based on the number of pages, then yeah, it should be 0 because it would be a perfect correlation. I intended this more as a scatter plot. So A is the answer I intended, but there are quite a few people who said D, and maybe you were thinking of it as though it's perfectly predicted from sort of algebraic equation. So that's why this one, because of the phrasing, is technically correct. Okay, but hopefully the overall point is clear. Questions on that? Okay. Let's look at the next one. Okay, so this goes back to that data set, and you can figure your best answer here. Okay, so we are, there's a number of ways we could approach this problem. I mean, you could actually create the scatter plot on your calculator and kind of figure out intuitively, if you added the other ones in your head, what that would do. Maybe one thing of thinking through this real quick without having to go into a lot of detail or a lot of difficulty with it is if we've got our x going from 0 to 20 right here, and we don't care about what the y values are, but it looks like the original data set right here goes from 1 to 11. So all your original data falls in this range about right here. So the very first thing that I would focus on is this high leverage. So high leverage would mean it would need to be outside of this. You really can't go any further left. We'll assume we can't. So we just want to look for points that are further to the right. And the 5 and 2 fall right in that range as far as where the data already is. So those are not high leverage. So B or C are the only options. So now we just need to figure between those two, which one is going to be an actual outlier? Which one might fall in line with where we predict it to be? So I don't need to necessarily plug it into a regression equation, though if I had this in my calculator and I calculate the regression equation, I could figure it out, which one has a bigger residual. That can be time consuming. Hopefully you can kind of get an idea. We start at, if we say that about 40 is about up there, and we come down to about 27, you know, whatever that is. Okay, it looks like as we get further along, it's going down. So at this point, 2012, that seems like it's actually in line or close. 1940, wow, that's going to be way up here. So that one is an outlier. So there we go. 1940 would actually be your best choice here. All right, we've got one more multiple choice question. And then we'll look over an FRQ, and then that will do it for the day. So take a few minutes on this one. So with this one, what we've got is, we went through a problem like this before, but it's worth seeing it again. If we have an actual data point, someone 67 inches tall weighs 135 pounds. So that's real data, but we want to figure out what the residual for that is based on the model that we were using to predict weight. Now, there was a good question that was asked earlier in a different class where someone was like, you know, getting confused by these, the pounds and the pounds per inch, all this stuff. Remember, these are the units that we're using for our slope, units of y over units, 1 unit of x. And then we've got the pounds, which is a unit of our y variable. So anyways, just keep that in mind, but let's kind of go through and calculate what the predicted weight was going to be. So the actual height of this person is 67 inches tall. So I'll just call it y hat right here to save on time. So negative 120 plus 4, we don't worry about the actual units. I'll just put 4 times 67 is the height of this person. And we can actually plug that in. You guys already did the math. And when you do that, it's 148 pounds. So the predicted weight for someone 67 inches tall is 147 pounds. That's not my final answer. What I can do now is I can use my residual formula. I can say, well, the residual is the actual minus the predicted. I know the predicted is 148. I know that the actual, now we use this number, the actual is 135. So when I do that calculation, that's going to give me a residual of negative 13. So the correct answer here is B. And that's what I believe most people got for that. So pretty good there. Okay. So any questions on stuff we've covered so far? Again, questions are there. You can chat them. You can chat them at me, or you can hang out afterward and we can talk about stuff. So we're going to look at this FRQ there's, it looks like there's a lot going on, but a lot of this is stuff that we should be able to quickly look and analyze. So I know it's hard to read it, but basically the Great Plains Railroad is interested in studying how fuel consumption is related to the number of rail cars for its train on a certain route between Oklahoma City and Omaha. Ooh, that's scenic. A random sample of 10 trains on this route yielded the data in the table below. So we got our data table. We got the scatter plot. It already shows us that. We've got the residual plot. We even have a computer printout. So this is just stuff that we can refer to. All right. So I won't analyze it just yet. I'm going to see what they want me to do. So is a linear model appropriate for modeling these data? Clearly explain your reasoning. I am not going to write this down, but I will verbalize what I would write down. So to determine if a linear model is appropriate, I want to look at these two plots. The scatter plot, and this is where I might actually write this down, a linear model appears to be appropriate because the scatter plot shows what seems to be a linear relationship, and the residual plot shows an even scattering of data with fairly constant variance around zero residuals for the entire length. There's no obvious pattern in the data, and there's no extreme outlier that would throw off the linear regression analysis. And they are both quantitative variables, so that's appropriate. Now I might phrase things a little differently when I write it, but I'm kind of running through all the assumptions and trying to think what the other assumption was, if I've got that. Okay, no, I talked about all the assumptions. Quantitative variables, equal variance, linear appearance, and outliers. So therefore, I've kind of covered that question talking about it, and we're good. The next one. Suppose the fuel consumption cost is $25 per unit. Give a point estimate for the change in the average cost of fuel per mile for each additional rail car added to the train. Show your work. Okay, this one was I was struggling with this question earlier because this $25 per unit kind of throws me off a little bit, but we want to give a point estimate for how much it costs for every additional rail car. All right, so let's kind of think through this. And if we've got a slope of r, well, we already have the slope. We don't need to calculate it because the slope is given right here, 2.15. So I'll just, I'll go ahead and write the full thing out, 2.1495. All right, so if every additional fuel car, so this is saying unit of energy per rail car. So that's how we want to interpret that. And because of that, $25 per unit, well, now I can go kind of multiply its dimensional analysis here. So it's going to be $25 per unit. So if I just multiply those together, then that cancels out, and we've got 25 times 2.15 basically is going to be about $53.75 for every additional rail car. But that's entirely dependent on the slope, nothing else. Okay, now it says show your work, and showing your work means you want to verbalize what your thought process is. That doesn't mean just show this. Oh, I showed my work and here's the answer. Write a sentence. And I don't know if you guys need to see a sentence to make more sense of that, but hopefully it's good enough. R squared. We need to interpret R squared in the context of this problem. Remember, we have two R squareds given, but we use this one, not R squared adjusted. So R squared 96.7%. So we have a template for it, so you can refer back to this if you have a question. on the FRQ, but 96.7% of the variation in fuel consumption is explained by the model. And I just said it. I don't feel like writing it down at the moment. But that is, so I'll just say that again. 96.7% of the variation in fuel consumption is explained by the model. And I know it's fuel consumption that's I'm talking about because that's my why. Okay. And the very last one, would it be reasonable to use the fitted regression equation to predict fuel consumption for a train on this route if the train had 65 rail cars? And explain. So this is a question that's asking us to consider extrapolation. So we're going from 20 to 50 with our data, and they're asking about 65, so that would be extending our model. Now, would it be reasonable? We would want to say something to the effect, while our model could be used to predict it, the fact that we are extrapolating that far out means that there's quite a bit of uncertainty in the model, and it would not be the most reliable estimate. So you're kind of hedging it a bit. You say, yes, we could. Yeah, we could. Is it reasonable? Well, there's a lot of reasons why we might not want to. And so you just kind of talk about the fact that extrapolation leads to problems. Okay, are there questions on that FRQ? I can't emphasize enough that really with an FRQ, the whole point is to be able to verbalize, or not verbalize, actually write out your thinking so that people who are reading this, and in this case, it'll be me, I know that I can follow your thought process. I can't assume anything unless you write it down. Okay, so hopefully that's good. There is some in fact, I'll just move ahead now. There is some FRQ practice in the Canvas classroom. Now this time, I'm not gonna guarantee that one of those will show up on the test like I did with the first 2 unit tests, but regardless, it'll give you good practice so you can be ready for whatever is on the test on Tuesday. If you want to get ahead, you can read chapter 11, but focus on studying for the test. The only other thing I'll mention on the Canvas classroom, there's another worksheet. The Friday homework that you'll find, none of it needs to be turned in. So don't worry about that, but I do encourage you to look at it. It's a couple of PDFs. Go through all of it just for extra help, and then look through all the other homeworks. Complete all the other stuff you're supposed to, like turn in that Unit 2 homework if you haven't done it yet, which most of you have. Look at those that AP progress check on AP Classroom. And the AP contract, if you haven't signed that or you haven't reported to me that you've signed it, please get that done. So anyways, it's time for a 3-day weekend. So have a wonderful time. And if you still have questions, you can hang out. But otherwise, I'll see you on Tuesday.